Welcome everybody. So that's a special edition of, it's a special mini course by Sergei Ketov from Tokyo Metropolitan University. So Sergei is visiting the institute for 2 months, and his visit will come to an end in end of February. So he will be still here for a couple of weeks. And so today and tomorrow and Thursday, he'll give 3 lectures dedicated to cosmology. So Sergei, without further ado, I pass the word to you. So please, so this is a mini course actually aimed at students. So please ask questions, any kind of questions, I suppose.
Okay, thank you very much for the introduction and for invitation. It's my pleasure to be here for the first time. I want to say that in addition to this mini course, there will be a general colloquium on February 20. You saw the advertisement. It will be for general audience, but this mini course will be more specific. It is I designed it at the level of graduate students. I don't assume that you have special knowledge in cosmology on the one side. On the other side, of course, time is limited, only 3 lectures. So usually it is supposed to be done for semester, what I do in Tokyo. So of course I will skip many details or don't go to details or to calculations, but they're available also from me on demand. So if you are interested in, we can continue discussion. My room is 106 here. Okay, so the title of today's lecture is Standard Einstein-Friedmann Cosmology and its Problems. So it serves as a preliminary to the modern cosmology, why it's needed, and basically it will be upgraded later with inclusion of dark energy, dark matter inflation. Okay, so if you are interested in the literature, I have to disappoint you. There is no good book about modern cosmology because the subject is so rapidly developing that any book becomes obsolete pretty quick and soon. Nevertheless, for the entry level, the serious entry level, I would recommend one of these 3 books. Actually, I think my favorite one is this one, where it is from the scratch written and with great details. If you are interested in a more like a reference book, so I would recommend Weinberg, but it is not good for studies. It is good for references. And what is more closer to my presentation is this book, which is, of course, the list can be easily expanded. It's just my preferences. Okay, so I will stay in 4 dimensions. Sorry for that. Only in a standard picture for today, which is general relativity setup. I'm using these local coordinates, okay? So this is spatial coordinates. I use mostly plus signature and natural units, and I will use the reduced Planck mass, which is defined this way in terms of the Newton constant, and kappa is the inverse Planck scale. So as you are very well of, the standard procedure for the general relativity is based on the Riemann geometry with a metric postulate, which means that gravity is essentially the curved space-time, okay, described by the metric or by the interval. So metric postulate and symmetry of connection, you get Christoffel symbols. And from Christoffel symbols, you derive the curvature, for example, the commutator of covariant derivatives. And from this curvature, you can build Ricci tensor and scalar curvature, which is a standard setup of general relativity and which is everywhere in every textbook. So my question is, my intention is to apply this setup to the whole universe. Okay, so so I'm going to talk about cosmology. So cosmology is not about everything. Cosmology is about the large-scale structure of the universe. Okay, so for example, this means how large. In physics, you have to specify. And this means distances, relevant distances beyond 100 megaparsec, which is, for your feeling, it is just much bigger than the distances between clusters of galaxies. So the structure, like galaxy structure and cluster galaxies, appear at the level of kiloparsec, so which is well below 1 megaparsec. We are talking about 100 megaparsec. So this means it is, of course, very different, because when you look at the such a large-scale structure, I mean, in terms of observations, okay? The observations, where they come from. You can, for example, consult NASA, but it's, which was a standard reference, but there are also more references like Sloan digital survey. It's like a Googling of the universe. There was a Planck satellite mission in the past, and more recently there's a Atacama telescope and South Pole telescope, which deliver actually rather precise information, which we discuss later. So of course, once you have a general relativity, it's quite natural to apply Einstein equations to the whole universe at such scales. So let us consider these Einstein equations. And I just remind you that one of the basic properties of our universe is that it is expanding. It's not just static. And if you see, which is, so the speed, kinematical speed with which stars, for example, running away from us is proportional to the distance, and proportionality constant, so to say, is called Hubble constant. This was known for 100 years. And this is a very important fact, that our universe is not static, okay? But from that, if you just assume the linear development, you can immediately get the age of our universe, yeah? Because if you just write U as the R over T, so R cancels and you get the inverse Hubble just the age of our universe. This is an important issue because it means that the age of our universe is finite. And by measuring Hubble, you can get the age of our universe, okay? So there is some tension about the value. It could be 74, it could be 68, but I will not go into details in so-called, it's not important for us. Good, so besides that, what is a very important fact about the large-scale structure is that our universe at large scale is highly homogeneous and isotropic. This is important because if you look at this table surface, yeah, it also looks isotropic and homogeneous, every point the same, every direction the same, but if you take electronic microscope and go to details, you will see it is not homogeneous and not isotropic. There are atoms, molecules, and so on. So it is a serious story. Okay, so then the question besides that, what is the source of experimental information we can get from our universe from early times? The standard source of information, so-called cosmic microwave background radiation, which is relic radiation, which originated about 400,000 years after the birth, because before that, photons were confined through that. Because of Thomson scattering, they were not free. But once the universe cooled down enough, they become free and fill out the whole space. So we can measure it, yeah, and we can measure it in a very detailed way. So this will be the primary source of information because this is the earliest signal we have from the early universe. At present, the temperature of CMB is about 3 Kelvin. It is not completely homogeneous. Yeah, there are fluctuations of temperature, of density, which is about 10 to minus 5, and contribution to the rho or to the omega of universe is small but not negligible. Okay, so it's called microwave because the peak of, if you consider the spectrum, the peak of radiation in the microwave region. Good. So another question is whether Einstein theory, which is a classical theory, is good enough to describe early universe. Yeah. Then we should look at the Planck numbers. Okay. So Planck numbers in terms of centimeters second and energy. And so if you are far away from this, you can use classical gravity. It doesn't mean that it was not sensitive to quantum corrections, but you don't need quantum gravity. And this is good news because we don't know quantum gravity. So this is incredibly high energies, because if you just compare the top energy of LHC, it is just a huge difference, okay? But on the other side, if you are far away from 10 to minus 43 seconds and minus 33 centimeters, you can safely use classical picture, in particular space-time. Okay, so but when you have the Einstein equations, you have left-hand side, which is the geometry of space-time, it's clear, but on the right-hand side, you have energy momentum tensor of everything, including us. Okay, so question is how to really apply it. So it means we need a models, okay? And models basically means you have to put on the right-hand side of Einstein equation some ansatz, yeah, which depends upon several parameters, and the easiest ansatz is called perfect fluid, which is essentially two. It doesn't mean it has to do with fluid, it's just a name. It means it has only two parameters, which is energy density and pressure, okay? So actually energy density and pressure, in this case, in the without entropy, are related to equation of state, so there are only two. So this equation of state is usually linear, like pressure proportional to rho, okay? And W is called the state, equation of state parameters, and here are some examples. If you take, for example, non-relativistic dust or cold matter, it's called P is 0, so W 0. If you take radiation, then this is equation of state, so this is a parameter, it is called hot matter. Okay, and if you take cosmological constant, we will go into more details, you will discover that pressure is negative and omega is -1. It's just a basic example. So usually one assumes, or one assumed in the past that there is nothing more than just a cold matter and hot matter, maybe cosmological constant, so this was a standard ansatz for a while. Okay, so another question is, which is pretty powerful, is that as long as you have a homogeneous and isotropic universe, it's the first approximation, this is a highly restrictive requirement. You can actually write a metric of such a universe, which is fixed by symmetries only, without using equations of motion, okay? So this is so-called Friedmann-Lemaitre metric. Actually, it depends how you call it. It depends upon the country to be politically correct. Yeah, in Russia you just say it Friedmann metric because he was the first who do it. But if you do it in France, they will complain. You mention Lemaitre, who did it several years ago. But if you do similar in America, Americans will complain because Robertson and Walker made it widely available much later. So politically correct, it would be called FLW metric. Okay, so what is this metric? This metric actually, what is remarkable, it depends only upon a single function of time. Basically, this is just a consequence of a uniformization theorem, but it can be derived by using Killing vectors. For us, mostly important case will be k equals 0, as you will see later. I just only want to mention here that doesn't matter what this cosmic factor R is, the Wald tensor built out of this metric is 0. Curvature is not 0, but Wald tensor is 0, so this means it's conformally flat metric, so you can transform it into the conformally flat case form, which is just proportional to Minkowski metric. Okay, so this done, for example, in the case K0, you go to conformal time like this, and metric becomes conformal. Another important consequence of this is that the Hubble constant is not really constant if you use this setup. So it's actually dependent upon the cosmic factor like this. But astronomers, they don't use this. They use what's called redshift Z, which is defined as this way. And particularly for CMB, Z is pretty high. Okay, so well, from a mathematical point of view, this statement is just nothing but the uniformization theorem, because if you homogeneity means that the space time is a coset, and it has to have SO3 stationarity symmetry, and so you have to fix G, yeah, which must be 6-dimensional, and there are only 3 possibilities, so that's how you get it immediately. Okay, so I hope this is well known, and I have to tell for if there are no questions, this means I assume that it is a kind of trivial, or you know very well. I try to accelerate. So then if you have some problems, please ask questions. Yeah. Okay, so I want to, before I go, I want to define so-called maximally symmetric spaces. These are not, these are very special spaces. So maximal symmetric space means that curvature proportion to the metric like this, where the C is a sectional curvature constant. And again, there is a fundamental theorem that there are only 3 possibilities for such maximally symmetric spaces, namely Minkowski space, de Sitter space, or anti-de Sitter space. And it can be realized in several ways by using the Friedmann metric. Okay, so for example, one can use particular parameterizations. Maybe I stop it. Why it's called flat case? Because you can go back to the Euclidean coordinates in space. So I will mostly deal with this. Okay, so of course, the next point is just to put Friedmann metric into the Einstein equations with ideal fluid energy momentum tensor and solve them, yeah? So we need just 2 equations because we have only 2 independent functions. These 2 are related by equation of state. So usually one takes mixed components of Einstein equations and takes the this, which is a consequence of Einstein equation. So when you calculate this for the Friedmann metric, you get this. So you get this form. So this is called Friedmann equation. So as I said, for us will be important case K0. So this just means H is directly related to the rho. And this equation is nothing but the continuity equation or the first law of thermodynamics. You can easily integrate it. Yeah, you get this. And what is important for us is that once you use equation of state, you get the rho diluted like this. So for hot matter, it is 3, and for cold matter, it is 1. The message is that the density of radiation will drop faster. Okay, and this means that actually the universe will be matter dominated. So this means that we come to the natural story that it should be some kind of birth, yeah, then there should be radiation domination, then should be matter domination. This is a proof. Okay, I would like to also turn your attention to the consequence of Einstein equations, which is also has this form, which is known as the Raychaudhuri equation. This is the equation which determines the acceleration of the universe on the future, okay? And this is quite remarkable because this means if, in order this to be positive, yeah, which will be relevant for dark energy, this has to be negative. So this means P has to be negative enough to get this left-hand side positive. This means we need some kind of negative pressure. Negative pressure can be realized in 2 ways. If you are happy to live with some exotic matter, put it by hand, then this is a trouble because we don't know matter with negative pressure, but cosmological constant easily does the job because in cosmological constant, P is minus rho. Okay, so this means this is easily satisfied. Okay. Yes.
And this equation is valid for which value of the K, Euclidean, hyperbolic, or spherical?
Well, I use just spherical case also always, but this is also true for any K. Well, as I said, I will be interested in the early universe only. Then K is 0 only. So this is a valid question, but this is definitely true for K0. Okay, so next we can just get solutions in a full form, but I don't want to write it to bother you. I just concentrate on K0 case. You will see why later. And you see that A, from this exact solution, you see that A is, develops like square root of T, but rho develops at T minus 2. And also for the matter domination, you have the same story, which means if you go back in time, you get a singularity at T equals 0. Yeah? So this is, means setup is broken. You have to use quantum gravity. But after this 10 to minus 43 seconds, say several orders of magnitude, you can do that. So I'm never going to address the issue of singularity. It is a different issue because it requires quantum gravity, but quantum gravity, we don't have experimental input. Okay, so just want to tell you that if you are in the times like 10 to minus 38 seconds and later, you are safe to use classical picture. Good. So just to mention a little bit about cosmological constant. Yeah, cosmological constant, you just add this term to the Einstein tensor, or you add to the right-hand side. Important is that pressure automatically negative for positive cosmological constant, so it allows you to have acceleration. Actually, negative cosmological constant leads to the collapse of the universe very quickly, so it is not realistic for our universe. And for the early universe, again, cosmological constant will be irrelevant because when I show you its expected x values, and it is so small. So basically, the standard textbook about general relativity tells you that we have a singularity, then we have a radiation domination, we have a matter domination, and then we go home. So this is just introductory course of general relativity usually finishes on that. Good. So this is my setup. Now I'm going to criticize this setup. So what are the important? Well, first of all, let us introduce a critical energy density by definition, yeah? And actually, in terms of Hubble, I always consider the contribution to energy density, energy budget in terms of omegas, which is a ratio, not rho, because this has no dimension, okay? Then the Friedmann equation can be written like this, and if K0 is just omega 1. Okay, so then there is a problem because actually omega 1 or close to 1, it is a, you can set it of course by hand, but the problem is it is not a stable, it is not a fixed point. It is there is an instability. So this means you have to require that omega is extremely close to 1. Just to exemplify this, if you look at the, sorry, did I? It's here, yeah. Yeah, if you look at the solutions to Einstein equation, you see that it is proportional to t, so it's growing with time. So it means this is an unstable critical point, and therefore, since we can measure omega now, which is very close to 1, it means in the early universe, it has to be extremely close to 1 in order to meet observations, okay? So, for example, in the case of, oh no, this is, for example, in the case of BBN times, sorry, this is a bit, I have to, no, it's a bit, there is a delay, I'm pushing too often. Yeah, for example, at the time of nucleosynthesis, 3 minutes, yeah, it has to be extremely small. So this is a extreme fine tuning. So the question is why it happens. So you have to, it means that Friedmann universe is a highly exceptional universe. Such universe has a measure 0 in terms of all possible universes. So it's very surprising that we are still alive and our universe is still alive because it is highly special situation. So there must be a reason to omega put to 1 in the early universe. This is usually called a flatness problem. Okay, so this is what I emphasize. But there is another problem, which is called horizon problem. Horizon problems comes from analyzing the pattern of CMB. Because on the one side, when the universe is expanding, yeah, we should look not only into the expansion, but also on the causally connected region. Causally connected region, which is called Hubble radius, so it is h-1 over a. So you may ask, so you should expect that the CMB pattern has to be the same inside causally connected region where any points could talk to each other. But if you have the situation, which is really happens, that CMB pattern is the same also in apparently causally disconnected regions, this is a problem because how it could be that you have the same CMB in two points of a universe which were not causally connected to each other. This is very unreasonable, okay? This is called a horizon problem. Well, there is another problem which I will play down because it is goes to particle physics, but it is not really serious, can be solved later, about overproduction of monopoles. But there is an even more fundamental issue about structure formation. By definition, a Friedmann universe forbids any structure. It's by definition homogeneous and isotropic. So the question is where the structure comes from, where, how particles come from, how the stars, galaxies comes from. So you have to provide the mechanism of structure formation in addition to the, which would be connected to the Friedmann universe approximately. But this is also missing in this standard picture. So maybe I just, yeah, here I started talking about some details. So the main point is that omega-1, which we observe, is a huge fine-tuning. So this has to be explained. This is a flatness problem or age problem. Another problem is that horizon problem. The point is that the causally connected region is defined by the Hubble horizon, like that. And for example, so it is much less that the region could be observed in the early universe and the present universe. For example, I just give you some number maybe. Yeah, so CMB radiation covers this, but causal region is this. So you have to explain why CMB is the same beyond this boundary, which are apparently disconnected. They have to be connected somehow. So this is called horizon problem. Of course, this assumes no acceleration. So the solution to this would be just if we assume acceleration in early universe, but very fast acceleration. Actually, this is the origin of inflation. Okay, so you see, this was known or discussed also 45 years ago, but when they didn't have any experimental input. They were discussing internal problems of general relativity, Friedmann universe, and they come to this list of problems. Now we have observational input, which makes situation much better because we have numbers also. Okay, so about monopoles. Well, monopoles, let me skip. I think I don't have time for that. So the intermediate conclusion is that it is apparently incomplete picture. Yeah, it doesn't explain the original structure. It has problems of horizon flatness. Okay, and also it doesn't address more recent developments, namely dark energy, dark matter. Actually, in some sense, the need of acceleration is important, but it doesn't provide the tools for that. Yeah, so that's what we need some upgrade. We'll be talking mostly about the early universe cosmology. Okay, so what are the main pillars of modern cosmology? It is dark matter, inflation, and dark energy. So my lecture tomorrow will be devoted by inflation. Today I just discuss observational stuff for dark energy, dark matter to provide the basis for more detailed discussion. Okay, so probably you saw this picture, everybody, that the history of our universe in one slide from NASA. It looked like this. So you see this line, yeah, this is acceleration, okay? And in order, this is a CMB, okay? And in order to explain CMB, we will need inflation. And where the data comes from, it comes from satellites like WMAP and others, which measure CMB pattern at present. Good. So I want to summarize observational evidence in a very short way, just by matching the data from different experiments like baryonic acoustic oscillations, supernova, and CMB. So the outcome of this is a famous diagram which shows you a quite remarkable result that you have the most of the energy budget of the universe is allocated to the dark energy, and visible universe has only a few percent. Yeah, so this is a remarkable development, because the very fact that of dark energy looks very unnatural from the physical point of view, because it just means that when you should expect dilution, yeah, and deceleration, but observation shows the acceleration, which is very strange and naively. Okay, so the evidence is huge. It's not my purpose to, I'm also not probably a good person to discuss experimental stuff, but I want to say that the outcome of this can be summarized, as you know, in terms of cosmic pi, which shows that the dark energy essentially occupies about 70% of the energy budget, 25% is allocated to dark matter, which I will discuss, and only 4 or 5% are allocated to any visible matter, including all stars and galaxies. Okay, so there are a lot of reasons for dark matter. I just remind you the basic reason. The basic reason, which was probably the first one, is not I'm not sure the first or not, but it is very convincing, because you know Newton Kepler laws for solar system. So if you apply them naively to the galaxy, assuming that in the center of the galaxy there is some kind of compact object, say supermassive black holes, and galaxies are moving around like point particles, you should get the dependence velocity of the distance like according to the Kepler, Newton, but in reality it's like this, which means it is more like a disk. And this means it has to, interstellar space has to be, intergalactic space has to be filled with something which is look like make it solid. Yeah, so this is called dark matter. So dark matter is needed to keep galaxies together, basically. And you have to explain this, of course. So this is where dark matter comes from. And of course, it shouldn't interact electromagnetically. It should also be stable or quasi-stable. And from astronomical observations, we can figure out the density of dark matter, which is about this. So it's essentially 3 protons per cubic centimeter, something like that. Okay. Just also important to get some feeling. You may say, oh, if dark matter everywhere, why we don't see it here? Why we don't see it in the solar system? Because in the solar system, we have a precision experiments which don't indicate on the presence of dark matter. This can be explained just by numbers. For example, if you take, since we know the density of dark matter, if you take the volume associated with our solar system, yeah, which is this, then you get so much of dark matter. Okay, if you just take, say, Earth's orbit. But question is, how is it big or small? You have to compare with the solar mass, and solar mass is 10 to 30 kilograms, so it is just 10 to minus 18. So it's sort of miserable that there is no impact of dark matter in the solar system. But if you instead take a galaxy, for example, our galaxy, then the orbit radius of the sun orbit is like this, and the amount of dark matter will be like that. And this is already something, because this is already 30 billion stars like that, and in our an entire galaxy is usually this one, so it is 30%. So this is significant. If you take even more like a galaxy clusters, you will see that dark matter will dominate. Okay, so again, evidence for dark matter is huge. I'm not going to review that. It is not my purpose. I just want to say this is a fact, and there is a lot of evidence for that. And because of that, there is also a lot of search for dark matter within the last 25 years. This search can be classified into indirect, direct, or ultimate. Well, people try to get, if you assume that dark matter consists of some unknown particle, usually, yeah. So you just add particle, you can make your own model of dark matter and try to feed the data, yeah. But the most important message is, so far, that all these searches were unsuccessful over the last 25 plus years. Okay, so this means if I want a kind of intermediate reference about that, the main key issue is what is the physical nature of dark energy, dark matter. We have only gravitational impact of them, and we don't know this is one of the most fundamental questions in modern physics. Okay, so they said dark energy, we already know the acceleration. Yeah, so we can in the first approximation describe it as a cosmological constant. So the scale which it introduces is about 10 to minus 3 eV. 10 to minus 3 eV is pretty small scale, yeah, especially compared to the gravitational to the Planck scale. Another issue is the equation of state for dark energy. It can be measured. It was measured, but the current measurement just give you something around -1. So it means if tomorrow somebody discovers that it is not -1, it means that dark energy is not a cosmological constant, which is actually very likely from my point of view. But so far, it is open question. And as regards dark matter, in general, it should be cold, so non-relativistic, most likely non-baryonic, even though some people debate that. It should be stable, or at least metastable with a lifetime beyond the age of our universe. And there are many candidates on that. I will, for example, one of the most popular candidates was WIMP, assuming that dark matter is weakly interacting. Why it was popular? Because collider people were happy about such things because they may try to discover it on the colliders. It didn't realize. So WIMP is not a leading candidate, but still possible. Okay, and this is usually summarized at this level with a so-called standard model, yeah, like in particle physics, but there is a cosmological standard model or concordance models, which tells you that current universe is just lambda CDM, which means some small cosmological constant, and cold dark matter, we don't know which one. So this is almost state of the art in an observational sense. Okay, so what are the challenges? Well, first of all, suppose that tomorrow or the day after they will find out that the equation of state is not correspond to W minus 1. So it means it is not a cosmological constant. So the next natural option, actually, there is also some claims, not completely proved, that the dark energy also changing with time. So this means it should be replaced by it should be time dependent, and time dependent means it should be replaced by the scalar field. Such scalar field is called quintessence. So this will be natural possibilities. But again, once you assume that you have a scalar field, this scalar field has universal interactions with everything. So this means it will be naively in a clash with the solar system measurements, which deny any fifth force beyond strong, weak electromagnetic and gravitational. So you have to screen such a force due to quintessence in the solar system. It's possible. There is a whole branch of cosmology which is called chameleon cosmology. Chameleon from the guy from Australia changing colors, and the idea is that solar system has a relatively high energy density compared to intergalactic space. So you have to screen off quintessence in the areas where matter density is high. There is a modeling of this and the whole subject, which is called chameleon cosmology. I will not go to that. It's not my purpose. I will mostly concentrate on the early universe, but if you are interested, keyword is chameleon cosmology. Okay, another problem is that how to get structure. Actually, I will discuss it tomorrow, but the basic idea is that in quantum theory, there are vacuum fluctuations. If there is no gravity, that they are irrelevant, you basically take them out by normalizing the partition function. Yeah, Feynman graphs without legs. But if you have the expanding universe, you have to take into account of them because these quantum fluctuations are real in expanding universe. So, for example, in a usual without gravity, electron-positron pair can erase from the vacuum, originate from the vacuum and annihilate back. But if universe is fastly expanding, electron-positron appears, universe expanding, and they become real. Yeah, this is Schwinger effect. So this is a way how the matter can be produced. The idea is to generate structure for quantum fluctuation. But then you say, oh, wait a moment, quantum fluctuation are microscopic. We are talking about macroscopic structure formation. How it can happen? It can happen when there was a very fast, so to say, expansion of the universe at the very beginning. Very fast. We will make it specific tomorrow. And then you can generate macro fluctuations from microscopic. This is actually it was realized much later after inflation was proposed, but actually this is a main driver, main motivation for inflation now. Generate the seeds of structure formation. Okay, so there are some also problems which are called hierarchy problems, yeah, because for example this, yeah, but that's what often emphasized in popular talk, but I would play down it because this is not really an issue. Good, and so this means if we want to have structure, okay, we may generate seeds of structure, but we also have to show how the elementary particles create in the first place. So this means we need to not only inflation, but also particle production during inflation or after inflation. This is usually called reheating. So I will touch it later. Okay, so again, it's important that research is data-driven, because if you try to get a gravity from the pure thought, it's not likely that you will succeed, because string theory is an example. So it's very important to have the data input. I would say nature is smarter than all of us. So let us ask them, nature. So actually, right now, there are several projects which are targeting equation of state for dark energy, which is a crucial issue. Yeah? And for example, there is a Euclid satellite, which was launched several years ago. So the main purpose is to check this W, equation of state for the dark energy. I was last week in João Pessoa, in Paraíba, yeah, and they are building the device, which is called Bingo, which is the observatory, whose purpose is also to check dark energy equation of state through the baryonic acoustic oscillation. So Brazil is in the game, but after 1 year, perhaps, they're still under construction. Okay, so this is all what I want to say today. Oh, I was running. Maybe it was too easy. Sorry for that. So tomorrow I will talk about inflation in much greater detail specifically. Okay, so call it as a lecture -1. That is kind of setup. If it was too easy, I'm sorry. I think I finished for today. Yeah.
I think there are many things that remain unclear during the lecture because you skipped very fast.
But okay, we have time.
Maybe technical.
Please, yeah.
So,
okay, in the beginning of your talk, you mentioned that the old cosmology has a problem with monopole production, and then you said you wouldn't have time to discuss it. Now, since you have time, could you go back to that slide and talk about monopole production?
Sure. We have time, yeah. I was just kind of maybe too cautious. Yeah. So let me see. Yeah, monopole. So the point about monopoles, which was raised actually by Zeldovich and Khlopov in 1978, was the following. You know, there is in quantum field theory and the particle field, there is such a thing as grand unification. Yeah? So this means that the effective coupling constants of the weak, electroweak and strong interactions, they come together. And so there is no difference between them. It happens at the energies about 10 to 16 GeV. So this means that the standard model particle gauge group goes into one, so there's only one coupling constant, so it should be a simple group. So it's usually SU5 or SO10, yeah? So this is called grand unification, okay? This is a kind of fact, because if you run this coupling constants, they come together, yeah? But at the energies of 10 to 16, once you have grand unification, then it leads to the not only to the finite lifetime of proton, but also to the monopoles. And well, this is in textbook of quantum field theory. You can find that there are monopoles because of you have extra channels. So on the one side, there should be monopoles, which were predicted even by Dirac some time ago. Yeah, but on the other side, we don't see monopoles. So there is a clash, because if you naively put grand unification into this framework, there will be too many monopoles. Overproduction of monopoles, which is called. That's why it's called monopole problems. It is too many monopoles predicted naively. Yeah, if you put naively grand unification into this picture, and that's what I said, yeah, here. But there is for example, experimental bound. How many monopoles can be in our universe? They just 10 to minus 6 at the moment. So that you say, so you have to suppress monopoles, or don't let them to appear. And this will be, this was a problem in 78, okay? But what I will tell you later is that this corresponds to the corresponding temperatures of something like 10 to 16. But what I will tell you at the end of my lectures is that such temperatures and energies never happened in our universe. So this means grand unification never realized. It's just above the horizon. So at the reheating maximum 10 to 13 GeV. So this means even though formally the lines go to the one point, yeah, but our universe never reached such energies and temperatures. So that's why, even though mathematically grand unification is realized, physically it was never realized in our universe, and therefore this problem doesn't appear. This is us. Yes.
So the statement you just made that grand unification was never realized, is that
physically?
Physically, yes. Yeah. Is that consensus in the community, or is that a particular school?
No, I will argue why it's.
Okay, that's your theory.
Not only why. I will. Well, if if you go to the literature, there are thousands proposals, thousands models. Okay. And every theoretician defends his or her own theory or models. I will provide arguments why grand unification never happened. If it is new for you, please come.
It is. Thanks.
Okay. Yeah, it is not acknowledged. Yeah, by everybody. Well, even inflation not acknowledged by everybody. Yeah. So if I go to MIT or Harvard, people say, oh, there is a bouncing universe, of course, and blah, blah, blah. I will argue that inflation is necessary, and I will argue which inflation is necessary, and I will argue more about why I think grand unification never happened during the course. And this is our group, what we advocate, yeah. It's not my point of view only. I will provide some reasons for that, but not today.
So maybe following up, can you remind why monopoles are relevant in particular for cosmology and nucleons?
Well,
why they become a big
monopole? Well, you know Maxwell equations, okay? So what was the story? Dirac assumed that there are monopoles. And monopoles follow from the assumed duality. If you generalize Maxwell equation by duality. Yeah, duality exchange E and B, magnetic charges with electric charges. This is so if you make electromagnetic equations self-dual, yeah, then it requires magnetic monopoles. You may say, why duality? Well, string theory actually requires duality, and this was a very profound consequences of to physics. Okay, so this is one thing. Another thing is monopoles are required by grand unification. This is a second thing, yeah. But this is in a clash. We don't see any monopoles in our universe. And moreover, they have a very serious bound that they, if they exist, they contribute very little, if they exist, okay? So, but again, if you assume that grand unification happened, then you get overproduction of monopoles. And this is in a clash with observations. So you have to explain why there are very few monopoles, if any, in our universe. So my explanation is that grand unification never happened in our universe.
So I guess.
But this just relies on the existence of the maximum reheating temperature and inflation scale, which are open, by the way, for the moment. But I will argue what they are. They are lower. They will be about 10 to 13 and 10 to 9, not the 10 to 16. Okay, but again, this will be in order to convince you, not just, I don't want words. You will see tomorrow, I have to introduce inflation. Then you will see more specific argument, actually, rather, you will judge why it follows from our view on inflation.
So I'm a bit worried about the technical part, how much that would...
Well, there will be, second lecture will be more technical because I did not, I just quote essentially the textbook's information and showed you the problems. So we have to address these problems. Let us start addressing them tomorrow. But for that, I need inflation as a key element.
So, you presented the problems of our current cosmological model, but I had a hard time understanding why the flatness problem is exactly a problem. Like, it is really a fine-tuning that our universe...
If you have physical quantity, which has to be fine-tuned by 16 orders of magnitude, you think it is not a problem. Just slightest change will destroy your picture. This is a problem.
Yeah, I get that. It's a really fine-tuning, but what's stopping us from just accepting that we live in a indeed flat universe, like it is what it is?
Yeah, good. So your question can be put in this way. Is omega generated by physics or it's just environmental? So exactly. So there is another universe which is omega not 1. What I'm saying is that inflation gives you an answer why omega has to be 1.
Okay. So it will be answered tomorrow.
Yeah,
I guess. This question.
Yeah.
Okay.
So this, I put the problem. I didn't give you an answer. I will show you that inflation solves these problems, which I mentioned, namely why universe is flat and how the structure appears. Yeah, that's why inflation is so important. Okay. So of course, a priori, you don't know whether something is environmental or fundamental. For example, you have a cosmological constant. Yeah, is it fundamental or environmental? This is a huge discussion. Yeah, if it is 10 to minus 120 less than m Planck to the 4, you had a hard time to get such number from any physics. Okay, so you may say, oh, it is just environmental. That's what string theory tells you. Okay. In our universe, it's omega this. Lambda this. In another universe, it's another lambda. So that this is not explanation. Yeah, this is just so it is just multiverse environmental. Yeah, but of course, as a physicist, we want to know what is fundamental, what is derived. Yeah, And omega will be derived from inflation and as a consequence. So this is a reason, one of the reasons for inflation. And this is a strong thing. Yeah. So you can't explain everything, but the more you explain, the more you understand. Yeah.
I think that as someone who doesn't understand inflation so well, I get the flatness problem as like the flatness coincidence.
Yeah, I'm saying it is not coincidence. Yeah. That's why I'm going to devote the whole lecture about inflation specifically, not just mention it.
Nice, thank you.
Tomorrow, as I promised, yeah.
I understood for your that the value of the cosmological constant is very small in Planck's unit of energy, something like that.
10 to minus 3 eV, yeah.
10 power minus 120.
Well, it's better to talk about, this number is exaggerated. I think it's better to talk about, compared to neutrino masses, for example. Neutrino masses have also small. They're also small, maybe 10 to the same scale.
But my question is, what should be a suitable value from the quantum gravity theory for the cosmological constant?
Okay. So the usual assumption in popular book that if you have gravity or quantum gravity, the only scale is the Planck scale. So when you try to build cosmological constant in terms of Planck scale, you get this horrible number 10 to minus 120. But who told you, or they assumed, that Planck scale is the only physical scale? It's not. There is a cosmological constant scale, there is an inflation scale, there is a electroweak scales. So it is not fair to maximize this problem by appealing to the only one fundamental constant. This is a misleading. I hope I answered.
And I'm trying to move the discussion a little bit closer to technical details. So we have 3 minutes still. So, so we talked about omega, right? So I think
we talked about omega, yeah. But
to remind again the students what omega is, right?
So, omega is a total. It's just that rho total in the universe is equal to rho critical. So our universe corresponds to K0.
Critical is? I mean, I'm afraid there might be difficulties on a very basic level, right? So,
well, I didn't prove it, yeah. So, but I mentioned the problem.
Talking about definitions, so we're using here different letters appeared. So
no, omega is okay. Maybe I was to thank you for this. Thank you for this. Wait. Just a moment. Maybe I was too. It's just. Yeah. Oh, okay. So we talk about energy densities of various species in the universe. Okay. So first we introduce the critical energy density, which is motivated by the Einstein equations. Yeah. So rho critical is defined in terms of Hubble. Hubble is observable. It's this rate of expansion of the universe, okay? So you can take current value of H, which is measurable, okay? You get this critical agency 10 to minus 29 gram, yeah? So we will measure contribution of any species like monopoles, like dark energy, dark matter, not in terms of rho, but in terms of ratio of rho with respect to rho critical. This is called omega contribution, okay? So this is definition, omega. And what observations tell us that omega is very close to 1, extremely close to 1, total omega, which includes all contributions from all species in the universe. I hope this is very precise definitions.
It's about any other letter on this slide.
And moreover, Friedmann equation tells you that omega has to be 1, but it is not. It is unstable. So you have to enforce that omega is 1. And so we have to enforce that the early universe, now it's omega close to 1, but since omega goes away from this time, from 1, at the early universe, it has to be extremely close to 1. I just told you example. For in terms of nucleosynthesis, it is 10 to minus 16. This is huge fine-tuning. You have to explain it. What the idea was, just say omega-1 and go home. This is a problem. Of course, you can always say that it is environmental, so we close our eyes and go home. Yeah, it's like it's a philosophical issue. But what I'm saying, it is a physical issue, and it is a consequence of inflation.
More questions? That's it for today. Let's
okay,
thank,
so
Sergei again.
yeah, so hope to see you tomorrow. Thank you for your attention.